If I consider the case where I'm selecting certain objects from a pool and I essentially have only desirable and undesirable objects and I select them without replacement, then I can be using the hypergeometric distribution. This is how it works. I'm going to use an example where I've got 10 objects, 4 of which are desired and 6 of which are not desired, and I'm going to select them without replacement. So I will fill in this tree diagram for 3 different selections, understanding that the first time I select, I'll have a total of 10 objects that I'm selecting from. The second time I'll have a total of 9, and the third selection will have a total of 8 objects. So those numbers are going to be reflected in the denominators of my probabilities for each step. Now that this tree diagram is complete, I'm going to specifically look at the case where I have 1 desired and 2 non-desired. So 1 desired and 2 non-desired. And I can see that this path has that, this path has that, and this path has that. There are 3 paths. I can also see when I look at each individual probability that this path has 4/10 times 6/9 times 5/8. This path has 6/10 times 4/9 and 5/8. And this path has 6/10, 5/9 and 4/8. And what I'd like you to notice about these 3 different paths is that they have exactly the same number in the numerator and exactly the same numbers in the denominators. Even though they form different individual fractions, when we multiply them, because we have exactly the same numbers in the numerators and the same numbers in the denominators, they will come to the same final fraction. So now we need to work out exactly how many paths in every general case, the number of paths, and what the sum of these paths are. So I need to work out the number of paths. And in this case, it's 3. And there is a way we can do that. And then we need to multiply that by the value of each path. And we know now that the value of each path is the same. And therefore, we can calculate the probability that I have 1 desired item or 2 non-desired items, which is what I looked at. Now the total number of paths is nx, where n are the number of steps and x is the number of successes, if you will, that we're looking for. Now this nx equals n factorial over x factorial n minus x factorial. So if you don't know what a factorial is, we are going to have to chat about that, and we will do that very shortly. The value of each path we can generally work out here. And don't forget, we're going to have a fair bit of cancelling. So it's easier if you keep your probabilities in fractions. We know in the numerator we've got 4 times 5 times 6. And in the denominator we've got 10 times 9 times 8. And we're going to get our cancelling pen out and go to work. And we find that this equals 1 over 6. So overall, when we know that there are 3 paths and the probability of each individual path is 1 over 6, that our final answer, probability that we have 1 desired and 2 non-desired, equals 3 times a sixth, which equals a half. Now let's have a look at this factorial business to work out what that means. So let's have a look at what n factorial means. N factorial equals n multiplied by 1 less than that number, multiplied by 1 less than that number, multiplied by every number down all the way to 2 and then 1. Remember, we can often leave 1 out because multiplying by 1 doesn't do anything. Therefore, in this example, I had n equaling 3 and x equaling 1, which means n factorial, which is 3 factorial, will equal 3 times 2 times 1. X factorial, 1 factorial, is only going to equal 1. And n minus x factorial, which equals 2 factorial, will equal 2 times 1. So when I represent this fraction to find out the number of parts, and remember we knew there were 3 because we counted them, but let's prove that, I end up with n factorial, which is 3 times 2 times 1, over x factorial 1, and n minus x 2 times 1. If we leave the 1's in, we'll find that we'll have exactly the same number of terms in the numerator and the denominator. Then when I cancel out, obviously I can ignore the 1's, I cancel out the 2's, and I end up with 3 different parts. Now that works for absolutely any tree diagram with any number of steps, checking any number of desired outcomes. So if I had 10 steps and I was looking at 7 desired outcomes, I could use 10 and 7 like that, and I would end up with 10 times 9 times 8 and so on. But here's a cool thing about factorials. When I have larger numbers like 10 and 7, it may feel like it's going to be quite a cumbersome task. Remember, n factorial is going to be 10 times 9 times 8 all the way to 1. And then the denominator is going to be x factorial, so that's 7 times 6 times 5 times 4 times 3 times 2 times 1. And then n minus x, which is 3 factorial. And you can see because I've written the 1's, I have the same number of terms in the numerator and denominator. But now we get to cancel. And you'll notice that we can cancel huge amounts of this fraction. I've got 7, 6, 5, 4, 3, 2, 1, and 7, 6, 5, 4, 3, 2, 1. So there's a massive amount that I've already cancelled. And all I'm left with is this 3 that I can take out with part of the 9, and the 2 that I can take out with the 8. And I know that there are 10 times 3 times 4, 120 parts on a 10-step tree diagram. 10-step tree diagram has over 1,000 branches. There are 120 parts on that tree diagram that will have 7 desired outcomes. And that's how you can work out the number of branches on a tree diagram for any number of steps, and also how you can calculate the hypergeometric distribution, remembering that all the numbers that end up in the numerator are the same, and all the numbers that end up in the denominators are the same. If you found this or any of my other videos helpful, please subscribe to my channel or like the video. Thanks.